Today I will talk about Makie. Julia is a very fast, very performant language, targeting really high performance computing while still being very interactive, thanks to its just-in-time compiler. But plotting in Julia might not be Julia's strength. It's very powerful with some packages, but it requires a lot of compilation time. It has some drawbacks, and I will try to explain how Makie and its ecosystem of packages fits in this world of Julia coding. So what are our options to plot in Julia? Well, there are actually lots of them, and there are more than those, but I selected the ones that are actually popular, that have a lot of stars on GitHub, that are commonly used by the Julia community. There are, of course, more exotic ones. Plots.gl is kind of the entry point of plotting in Julia, the default for a lot of users. It's a great package because it's a high-level API that allows to work with different backends, such as the matplotlib pyplot or plotly.js or gr. So it's very convenient in that you write some code and then you can export using one backend or another. For instance, you can use Plotly if you need some interactivity, but gr if maybe you want some nice resolution PDF. But this one high-level API to export to a lot of things also has the drawback that people find that sometimes none of the backends really work, and it's particularly long. So there are alternatives when you can access some of these backends directly. For instance, there is pyplot.gl, which is a direct interface to the matplotlib.pyplot. So you can use pyplot in Julia through two routes. You can use plot.gl and select the pyplot backend, but you can also directly use pyplot.gl. And the syntax and the way they function are going to be different, but there are two different ways to access pyplot. Similarly, you can access plotly.js, which is great for interaction through the plots.gl high-level API, but also directly through the plotly.js.gl package. There is another package that's called plotlylite.gl, and this one is actually good to keep in mind because it's by far the fastest plotting option in Julia at this point. The time to compilation and the time to first plot are usually pretty poor in Julia, but this one is actually really quick. Now, the reason it's quick is because it has very little code. It's a very, very simple access to the plotly.js interface. And so the consequence of this is that it has fairly limited features. So that's probably not what you want to build some interactive plot for some fancy website, for some final project. But if you want to explore data, do a quick plot and quickly navigate your data as you're processing and thinking about what your data represents, it's really a fantastic option. For those who are familiar with the grammar of graphics, for instance, people coming from R, where Hadley Wickham really popularized it and improved it through the ggplot package, you may really like Getfly because it's based on the same grammar of graphic principle. And then there is also Vegalite, which brings this grammar of graphic to an interactive world. For those who come from the LaTeX world, there is something that might appeal, that is an interface to the PGF plots LaTeX package. And then there is this one. It doesn't always work fantastically. And of course, being all command line based, you can imagine that it doesn't exactly produce publication ready plots, but there is this Unicode plots.gl package, which is amazing because it plots in the terminal. So yes, of course, it's not going to create fantastic widget for a website or a beautiful a picture for your next paper. But one fantastic advantage, of course, it's super lightweight, renders instantly, even if it doesn't look amazing. But what's really, really cool is that if you use our production clusters, the Alliance clusters through SSH, because it's all in the command line, you don't have to worry about VNC or about X11 forwarding or about some client server system to see your plot directly. You don't have to save your plot to file and then copy it to your local machine, etc. You can directly see the result through the SSH connection. So that's pretty cool. So that's a fairly big world. And then, of course, there is Makie. So how does Makie sit in all that? So it's certainly not on the fast side of things when it comes to compilation and the time of first plot, which is the time it takes to run your code the first time while all the initial compilation are done, which can take some time in Julia and is particularly lengthy in plotting. So it's really kind of the opposite of plotly-light.gl. However, it is incredibly powerful. Once you have passed the compilation time, once you have run enough of your code that a lot of it has been processed by the just-in-time compiler of Julia, then really it shows its strength because it allows really a lot of GPU usage through OpenGL. It is fantastic for 3D. It allows animation. It can produce really high resolution thing. It can produce very large amounts of data. So it's not a quick and dirty tool, but it's a very powerful one. And then at the end, I'll have a little note about how you can handle this very lengthy compilation and time of first plot drawback of Makie.gl. There are options to lower that downside and take advantage of the upside of what it has to offer. So it is a very popular package. It's in active development. It keeps getting better. It's very popular, strong, and definitely worth playing with. So why am I talking about an ecosystem rather than a package? That's because there is the main package, Makie.gl, and that's a package that you actually never have to load into a session. And that package really contains all of the functionality of the package. It's it's the way the syntax and the functioning of this particular plotting system is coded. But then you have some backends. So what you will be using always are one of those backends to access Makie. So there are some variations. I talked about one high-level API leading to various backends at first when I talk about plots.gl, but this is different because while plots.gl indeed is a high-level API with one simple syntax that you can export to many backends, those backends are entirely different projects, which is why, while it's convenient, it might not always work very flawlessly. Well, this it's a very integrated ecosystem. So those various backends really are built on this Makie syntax. So it's a little bit different than the plots.gl way to access various backends through a similar high-level interface. So Kero Makie is ideal if you want a high-quality presentation ready plots for to save as PDF, for instance, or very high resolution things. It's amazing, but for now, it's limited to 2D. They might implement 3D, which would be fantastic for a number of reasons that I will cover later. But for now, that is one limitation. Another thing that's not a limitation per se, but a design decision, it focuses on the creation of the plot, not on its actual rendering. So if you are using Julia in some IDE, for instance, if you are using a Jupyter notebook, or if you are using VS Code with the Julia extension, or if you are using Juno, you won't have any issue because those IDE will provide a way to display the plots. But if you are simply running Julia in the command line, for instance, then, or if you're just running a script, you will be totally able to create the plots and save them to file, but you won't be able to display them. So one little tool that can be convenient to bypass this limitation is a little package that's called electrondisplay.gl, and it is based on Electron, the text editor. And it's a very lightweight package, and it will create some pop-ups to display your plots. So that can be convenient if you don't want to save your plots to file all the time, and if you want to get an update of how things are going. So that's a little quick and dirty trick. The fact that it really focuses on the creation of the graph and not on the rendering is actually extremely well adapted to working on the production cluster. On the production cluster, you probably don't want to do some X11 forwarding, which is extremely inefficient, and a very good workflow when you are using the clusters and running jobs is actually exactly that, to save your figures to file instead of displaying them on some window and then to use those files. So this is really fantastic tool for the cluster. However, it doesn't do 3D, and it is a little bit slow because it is not based on OpenGL as GL Makie is. GL Makie is the fastest of the three. It's the one that's the most performance oriented because it is really based on OpenGL. So it's really the GPU oriented one in the family. It does 3D rendering. It allows interactive plots. That's kind of the powerhouse of the ecosystem. However, it needs a GLFW window to display the plots, and you don't have to install anything independently. This is all, there is a dependency that's called glfw.gl, like a Julia package that allows to access the glfw, so this Windows system for OpenGL. So that's fantastic when you're working locally on your machine. However, this dependence it has on a windowing system makes it particularly nightmarish to use in the training clusters. Finally, there is VGL Makie. W stands for web. So that's pretty much a web version of GL Makie. It will do 3D, it will be interactive, it will use OpenGL and be fairly fast, but it is not as powerful as GL Makie and is more intended to use to create widgets and interactive browser tools that you can explore or that you can put on the website, a little bit in the line of plotly.js, for instance. And then there are some more exotic extensions, GeoMakie, and all of these are links, so you can explore that on your own later on if you want. That's really bringing GIS to the Makie world for geographical plotting. So that's really cool. That's something that I'm keeping an eye on because I think that could lead to a very, very interesting project. Algebra of Graphics is a way to turn the syntax of Makie into a very simple system where each part of a graph is considered a little block, and you can use very basic algebra like summation or multiplication to put your plots together. So it doesn't add functionality, it just rewrites the syntax. And Graph Makie brings to Makie the world of network graphs, nodes connected by vertices, that sort of thing. So this is going to be way too small for you, but the link is here. The link is from a cool book on Julia data science. The author of that book put two little cheat sheets for Makie that I think are pretty useful, one for 2D and one for 3D. And to get a little reminder of the various functions without having to dive into the documentation, I think that's pretty useful. So maybe bookmark those and also have a look at that book. It's a useful book. So for resources, there is of course the official Makie documentation. There is that Julia data science book. Chapter 5 is focusing explicitly on plotting with Makie. And then there is a project called Beautiful Makie that is really cool because it has a lot of examples of code snippets using Makie, and some of the examples are very useful to understand how things work, to experiment, and to get a sense of what Makie can do. So those are, I think, very useful resources. Now, VGL Makie and Kero Makie are easy to install. You won't have troubles with those. But GL Makie can really be challenging. I've mentioned already that installing it on the clusters is very challenging because of this window dependency, and I'll talk about that more at the end of the webinar. But it can also be challenging locally. If you have a dedicated GPU, for instance, you may have some issues depending on your system. Personally, I am on Linux. I use Arch Linux. I have on my laptop a dedicated GPU, and I did have some issue installing it. Alex on his MacBook had no issue. So it depends on your system. But this page is good to be aware of because it might help you troubleshoot what's going on. Just be aware that yeah, that can be a little bit of work to get it working. And I've seen a lot of threads and forum when I was having issues of a lot of other people having difficulties. But Kero Makie, which again is incredibly performant, just doesn't use OpenGL and doesn't do 3D at this point. This one is going to be no problem. So for many applications, I think Kero Makie is really a great option. But yeah, if you want full GPU force and something as efficiency targeted as possible, you should try to get GL Makie to work on your machine. So what are the actual fundamental syntax and functioning of this plotting world? It's a little bit different from other plotting functioning that I'm familiar with, such as the grammar of graphic. And it's not complicated, but I think it's worth spending a bit of time on because it's not 100% intuitive at first. And until once you understand the various objects that are created and how to play with them, it is actually really simple. But I think it's good to go through what those objects are and how to play with it slowly, because it will make any fancy code crystal clear. And then if you go to this beautiful Makie project, for instance, and you see all those amazing functions, or if you go to this chapter 5 of the Julia in Data Science book, you will see lots of examples, and they will make perfect sense once you understand that. So first of all, you need to load one of the backend. Here, for instance, Makie, and you don't need to load Makie itself. Makie will be loaded as a dependency. Similarly, you never have to install Makie on your machine, because when you will install any of the backends, that will automatically install Makie. So you can install 1, 2, or 3 of the backends, but there is no point in explicitly installing Makie in Julia or to ever load it. So the first object I'd like to talk about is it serves the function of a container object. It's called figure, and what it is really is the full figure we are trying to create. To create that figure object, you just have to run the figure function. So for instance, here I am creating an object fig, and I am assigning to it the output of the figure function. And what it does is that it creates this empty, of course, because we haven't added anything to it, figure. And if I look at the type of this object, well, it's a figure type. Okay. So you can customize this object in countless ways. For instance, you can change the background, you can change the resolution. And when you install any of the Makie backends, it will install color.gl as a dependency, and that will allow you to customize the background using, for instance, named colors, which is what I'm doing here. Gray 22 is a named color. You can see the list here, and that will work out of the box without any problem. If you want to use some CSS specification, for instance, the like the eggs code for some color, if you're used to HTML and CSS, that's something that you might prefer doing. Then you will need to explicitly install colors.gl, and then you will need to explicitly load it. Why do I say explicitly? Julia is a bit interesting in this way. If you install a package, for instance, Makie, it will automatically install a number of dependencies. One of them is color.gl. So color.gl will technically be installed on my machine. However, if I run using color, Julia will complain that it is not installed because it hasn't been installed explicitly. And if you go to your Julia environment, which by default is in your home under .julia, and if you go to the environment and you look at the manifest.tom and the files that are there, you will see the difference between packages that are explicitly installed and packages that are dependencies. So to use the eggs notation, you need to explicitly install color.gl, which will allow you to load it. And then if you go to this link, you'll see that it has a huge amount of capability and can play with RBG and X and all sorts of notations with color. That's really the Swiss Army knife of Julia when it comes to colors. It's a great package. And here you can, using this colorant and then the X string, you can get the background modified. Okay, so first object, we saw the figure. Second object we'll talk about is the axis. You create an axis with a function axis, and you need to pass to this axis function a figure that you have already created or by running the figure function. So if you run this, you will get this very surprising output. It won't plot anything because you can't plot an axis. What you plot is a figure. So if you try to print this axis object, you will get a description of the structure of what is contained in this object with the mesh of all of the elements, etc., etc. So the type of this object is an axis. Here, note that I pass my figure that I could have created a figure object and put it here. Instead, I'm running the figure function, same thing. I'm putting it in axis, but I am also using some kind of indexing notation. And this sets the layout of your figure. So what does that mean? Let's go through an example. I created a number of figures. So my first figure was just, my first figure object was fig. I created by running figure. Then I created fig2 where I changed the background and the resolution. And then I created fig3 by changing the background. Okay, so there is this figure object called fig3 that already exists in my environment. It's the figure. Okay, so I am going to use it here. I'm going to pass it through the axis function, and I'm going to use this weird indexing notation with 1, 1. So what 1, 1 represents, they represent row and column as in a classic indexing notation. But what it means is that this axis will use 1 out of 1 row and 1 out of 1 column. So basically it uses the entire layout of my figure. So my axis fills in the layout. If I print it, this is what I have. So by running axis on the figure object, I have transformed my figure object. Even though axis doesn't have the exclamation mark that mutating function in Julia typically have, I think maybe the syntax would have been more consistent with the rest of the Julia world, but it has transformed my figure object because now it has an axis. Now look, for instance, so remember that fig was my very first figure object that I created. Instead of running on a figure object 1, 1, if I were to run 2, 3, well, this is what happens. So of course you would never want to do that on its own because this is not exactly a very great layout, but you can see that now my axis has been created on the second row and the third column. So you can already guess that this is going to be great if you want to create a figure with a complex layout in which you have a number of plots side by side, one under each other, etc. So this is a really super simple, super efficient system to create very complex layout. And I really like that because in a lot of the plotting packages that I'm familiar with, for instance, in R, the ggplot and the like, you need some additional packages that are often kind of awkward to create some fancy layout. And when you want to write a paper, usually you want a fairly fancy layout to have a number of plots organized in the same figure. And this does it in the simplest possible way. So here, for instance, remember that we had already transformed figure 3 by creating a first axis that was row 1, column 1, so it was using the entire plot. So figure 3 already has one axis. I mean, I said plot, I should have said figure. Now, if I run this figure 3 object into the function axis again, but with an indexing to 3, this is what I'm going to get. So this here is the axis I created before, and this is the new one that I am creating on the second row, third column. So this means that you can add new axis into a figure and kind of organize your layout in this very efficient way. And your axes are customizable as well, of course. So here I'm creating a fourth figure, and then I'm passing it to axis. This time I'm giving it the full layout. You can set an X label, a Y label, some title. Of course, you can change the font size of these labels. You can change the number of, I forgot what they're called, but like the number of little reference bars that show the various units, their tightness, etc., etc. And then finally, once you have your figure and your axis, well, you can add an actual plot. And there are a number of functions for this. So here we've created a figure called fig, then we're creating an axis called ax, and then I am setting some variables, like x is going to be the linear range between -10 and 10, and it's going to be of length 20. So this is the start, the end, and the number of points. Y equal x. So this is a very basic function I've got there. So then here is the line that matters. This is where I am actually creating my plot. Remember that in Julia, functions that end with an exclamation mark are mutating functions. So they transform their argument. So scatter is going to create a scatter plot, no surprise there. It has an exclamation mark, so it's going to transform the object, the argument, the first argument that is passed to it. Note that the argument here is ax, it's my axis. And then x and y are my the actual data. So by using scatter exclamation mark, I am transforming the axis, and because the axis depends on the figure, I am also transforming the figure. And this is why I said that even though the syntax is fairly simple, it is a bit counterintuitive and a bit awkward. Because if now I print fig, I have the scatter plot that got added. Okay, so of course, there are a bunch of functions, as you can imagine. Instead of scatter, you can have scatter lines. And now I'm using y equals sin of x instead of y equal x. So a different function, and I'm using lines. So now I'm having a line. This dot here means that I am broadcasting this function to all elements of x. X is an array, and I am, so y is going to be an array as well of the same size, same dimension. And for each element of x, I am creating an equivalent element of y that is the sin of x. So this is the broadcasting notation. So this is not a very nice line because I have only 20 points. So I could bump up the number, and now I have a sin function plotted. Okay. Now, okay. That explains the various objects, but it would be very tedious if you had to go through creating for the figure and then the axis and then add plots to your figure each time you have to create a plot. You don't have to go through that. You can actually create a plot all in one shot very directly. So here, if I have my X and Y defined, I can directly run lines X, Y, and that will create the same graph. So note here that this is lines without the exclamation mark because I am not modifying an existing object. I am creating here a new plot from scratch. So what happens when I run lines in this fashion is that it creates all at once everything. And it creates it in a fairly strange way. It creates what's called a figure axis plot. If you run lines on X and Y, and you look at the type of the object you have created, it's a figure axis plot. So if you want to modify the characteristics of the figure, for instance, the resolution of the color or of the axis, for instance, giving it some label, etc. Well, when you use a plotting function that creates everything directly, you will have to change their characteristics in the function through this syntax. Figure equals axis equal, and those are named tuples. So this is why you have this awkward semicolon at the start. It just shows that these are named vectors. They only have one dimension, and this is not an array or some other thing. Now, if you want to transform a graph, for instance, we had a sin graph. Now, let's say we want to add a cos function on it. Well, you will have to actually decompose this weird figure axis plot object. So you could create your figure and then your axis and then one plot by modifying your axis and then another plot by modifying your axis. If you have already created a figure axis plot directly by, for instance, running lines x sin, and if you want to add a new graph to it, well, you have to decompose it by running this line. The way to extract the independent object figure axis and plot from your figure axis plot is to kind of decouple them in this way. Note that figure axis plot is not a tuple, even though the syntax is similar to the way you would decouple tuples, but it works in the same way. So once you have done that, you now have an axis object called AX that you can modify with lines exclamation mark and then put something else in there, such as the cosinus function. And then when you plot fig that has been transformed by lines exclamation mark, you now have a sin line and a cos line. Now, we talked about layout. Well, maybe you want to, instead of having both on the same graph, maybe you want to have them on two graphs side by side. So if you have that same function lines of x sin, you first have to decouple it into a figure, an axis, and a plot. And here we will create a second axis to which we will pass fig 1, 2. The first axis here will by default automatically be created as fig 1, 1. So now by using fig 1, 2, my second axis is going to be to the right of the first one. If I had used fig 2.1, it would be underneath, of course. And then I can modify this second axis with a cosinus, and this is what I get. So that's it. It's fairly simple, this syntax, but it's a bit unusual. And so I think it's worthwhile to understand it once and for all. So now let's look at some fancy examples, and you'll see that once you've understood the syntax, it's actually really straightforward. So an example in 2D, so it's using Makie, which is great for a fancy 2D plot. It's using linear algebra, stat space, interpolations, a bunch of stuff. One thing that I haven't mentioned is that particularly if you are loading multiple packages in the Makie ecosystem, the way to activate one or the other is to use the activate exclamation mark function from either Makie or Makie or Makie. So if I run this, I'm going to be using Makie, which, because that's the only one I've been loading, would have happened by default. But if I now load Makie, this is still what's going to be activated. So the way to switch to a different backend would be to run glmakie.activate, for instance. Okay, so here we have some function, but that's just to create the data. What really matters is the plotting at the end. So look what we have in here. We have a figure object that is created with some padding, some resolution, an axis with the default 1-1 layout. We have a heat map function, which is a function we haven't seen yet, but that's one of the plotting functions. We have some additional customization, hide decorations, hat spines, okay. And it's all passed into this with theme black, which is a way to overpass the default theme and set the theme black on the plot without having to customize the background and this and that independently. So this is what we get. So it's a fancy function, it's a fancy plot, but the code to create it was really very simple. Similarly in 3D, so 3D we need glmakie, so that you can activate with glmakie activate. So we create some data, and then here again there is a with theme dark, and then we create a fig, an axis with a mesh scatter. This is a new function. So here we create the mesh scatter directly and we decompose it. So this is the second approach we've seen, the more direct approach. Then to customize the figure, since we have created everything at once, and to customize the axis, we need to use this name tuple syntax with a semicolon. Then to add a second plot to the first one, we use the mesh scatter exclamation mark. We modify our plots so with X limbs and Y limbs, with high decoration, etc., which is why we have all these functions with exclamation mark, and this is what we get. So simple syntax, but very nice result. If you have a look at the beautiful Makie project, you will see countless examples that will really illustrate the way Makie functions. Now, I mentioned at the top that the downsides of plotting in Julia in general and plotting in Makie in particular is the time it takes to compile and the time it takes to plot the first plot. There is one option. It has its downsides, but it really helps with these delays. And I think it might really make sense to consider it when using Makie. It's to create a sysimage with package compiler. A sysimage is simply a file that contains all of the elements of your Julia session. So it's going to have all of the packages that you have loaded that have, of course, been compiled. It will contain your global variables. It will contain all of these things that take so long to run at the first time. The downside of creating a sys image is that, of course, you cannot update any package in your sys image. If you want to update a package, you have to recreate a sys image. So if you keep your packages up to date and update everything all the time, that might not be a workflow that works very well for you. But if you are okay to settle on some package versions for some time, then you can create a sys image, let it run for a while, and then really have a very efficient session right from the get-go as soon as this file is loaded to have Makie shows its power without having all this startup time that can be really long. So I talked a little bit about this at the start as well, but what if you want to use the Alliance clusters instead of using your machine? So Kero Makie, no problem, and you will want to save your graphs to file. Here, for instance, so the function is very simple. It's save. I am saving a figure because remember that the object that matters in the end is the figure to a PNG. You can also save to PDF, to SVG. You can set the resolution. You can really play with the setting to have a very high quality printed image. Now, of course, it's 2D only, and it's not the absolute fastest in the environment. GLMakie is the fastest, but I talked about the difficulty to have it installed through SSH. X11 forwarding is not something that you want to do in general because it's very slow, but that's the easy solution. It doesn't even work with GLMakie. So it's something that you don't want to do in general anyway, but there's no point even trying this with GLMakie. One of the options, of course, are VNC. And Graham in particular have some VDI nodes. So there's some, I forgot what VDI stands for, but there are nodes that run OpenGL in some graphical fashion. So that definitely would work. You can also try VNC. There's VNC Tiger. There are various other options. Some will work, some won't. And then there is something that I haven't experimented with because I'm not sure how to go about it in the production clusters, but that's something that I want to explore. There is this virtual GL project that allows to play with 3D fancy visualization using OpenGL. For instance, if you are in a headless or in a remote session. So that might be the best option, but I'm not sure how easy it might be to implement it on the cluster, and I will try to look into that. Another option, if you wanted to use to create 3D plots and to use OpenGL, if you give up on getting GLMakie to work in the cluster, is to use VGLMakie instead. VGLMakie was not designed to work on a cluster and optimize speed. It was designed with the idea of creating some interactive widget. So there is this GSServe-GL package that's a way to render plots and other things in a browser in a fashion a little bit similar to plotly.js. So it's not optimized for performance, but it's nice for exploring things. And mainly, it has a server client system that renders the plot not in the Windows, but in your browser. So you can use this in the production clusters and have it render on your browser. You might be able to do this directly without passing through GSServe.gl by creating some SSH tunneling to your browser. For instance, if you run TensorBoard on the training cluster, you can create some SSH tunneling to visualize TensorBoard on your browser while your machine learning, your neural network is being trained on the cluster. So this might work. But unlike TensorBoard, that is not a very heavy tool at all. So it just shows the evolution of your training. It's not a very intensive thing. Here, your browser will have to do a lot of image processing, and this might not be the most efficient either. So probably the best approach, even though VGL Makie is interactive, is to save to file and just live with that. So for 2D plots, go with Caro. 3D plots, go with VGL Makie, but in both cases, probably best to save to file if you're using the clusters.